So if you know the oxygen content in your flue gases, you can estimate how much excess air you are having uh, in your fuels, in your combustion or flue. So if you have 4% excess oxygen in the flue, products of combustion in the stack, you are at about 20%. But if you're at 10% oxygen, you're looking at about 80%. So the first step you can do, even though this is not we want to talk about today, we are talking about design, but if you're monitoring any fired heaters, try to reduce the excess O2. It will help you get higher efficiency. Sorry, I had to switch on the light, it goes automatically. So minimize the excess O2. I mean, that's the operation guideline, but you should do it even for design. So this is a typical fuel gas our team has put together, has different components: hydrogen, methane, carbon dioxide, nitrogen, inerts, and you can see H2S. That's so very typical composition. I mean, in fact, in refinery, whatever you cannot sell or whatever you cannot process is burnt. That is the definition of fuel gas in refineries. Any hydrocarbons that you cannot sell or you cannot process is put in the fuel gas header. A lot of people put propane, butane because they have excess and they can't handle it. They can't put it into the flare, so they basically end up putting it into the fuel gas headers. Fuel oil, generally we, instead of giving chemical compounds, we give the elemental analysis, and it has carbon approximately around 81 to 86%, hydrogen 11 to 14, oxygen, sulfur, nitrogen, And as I said, sulfur could be anywhere between 3 to 5%. So why do we keep on talking about sulfur? Because sulfur is the villain. Sulfur is the one which prevents us from getting higher efficiencies. And what happens is, as I said, most of the sulfur gets converted when you burn, gets converted from sulfur to sulfur dioxide, but a small amount of sulfur gets converted into sulfur trioxide. And that sulfur trioxide, even though it is in ppm, it raises the dew point. Dew point is the condensing temperature of the flue gas. And if you can see my slide, you can see if there is no sulfur, the dew point could be as low as 138 or 130 And that means we should be able to cool the flue gases all the way down to about 150 degrees. And when you cool it down to 150, maybe we will be having efficiency of about 95, 96, even 97%. But you see over here in this chart, even if I have a little bit of H2S in my fuel gas, my dew point is already 240. So I cannot go down to those temperatures. So acid dew point or sulfur trioxide prevents me from achieving higher efficiency or limits me, and that is why we typically range around 91, 92% efficiency for most of the furnaces. This is a different thing, but almost same as sulfur, but this is for the fuel oil. And fuel oil is even higher, actually, when you look at it. Fuel oil goes even higher, So sulfur is not good for us. And typical recommendation is you don't want corrosion taking place in your air preheaters, in your ID fans, in your ducting. So you want to keep the metal temperature above the acid dew point, approximately 25 degrees margin you want to keep so that there is never. And dilute sulfuric acid is the most corrosive acid in the world. So you don't want to face that corrosion. So keep your metal temperature above the dew point. Similarly, the flue gas temperature, keep it above about dew point plus 75 degrees. So with these two restrictions, we cannot go down below 92, 93. Some places we have been able to go to 94. We will talk about that. But that's the maximum thermal efficiency limits we can achieve. This is again, we are talking about acid dew point. You can see excess air. As the excess air is increased, the dew point goes up. So the lower excess air, the lower excess O2 will help you get better efficiency. That's what we want to talk about. Hydrogen firing, we will cover a lot more in details, but hydrogen is very clean fuel. And if we can convert all our fired heaters to hydrogen, I think we will be absolute clean. Actually, we will be emitting water vapors. But I think the cost of converting heaters from current fuel gas to hydrogen is going to be prohibitive, and it will only take place when the cost of hydrogen production goes down. There is a sustained effort in US and in UK and maybe in India to little bit to start doing some experimentation and see uh, whether we can convert into hydrogens. So how do we reduce CO2? We talked about two things. One is maximize the efficiency, which means reduce the flue gas temperature to stack and also reduce the excess oxygen in flue gases. And the second one is changing fuel to fired heaters. That's what will happen in future. I hope it will take place, and we will be able to help you converting from natural gas to hydrogen. We can help you converting it from oil to hydrogen. Hydrogen is a very clean fuel. You all know that. But there are two things which are different. One is hydrogen has a very low density. It has a molecular weight of 2 as compared to natural gas. So it's very light. So what will happen? You cannot supply hydrogen in the same lines. You will have to re-rate, or you will have to check, because there will be a lot of pressure drop. From 18, when you go down to 2, the volume goes up by 8 times. So on a volumetric basis, the hydrogen heat release is much lower. And second is hydrogen has a flame speed of 10 times. So you have got to be very careful about hydrogen. You don't want any flashbacks. So these are some of the things which we will be looking in future when we start doing conversions. So let's talk about the thermal efficiency for fired heaters. There are so many parameters which goes into play when you talk about fired heaters. First is the fuel cost. We'll talk about that. Fluid temperature, process fluid temperature, sulfur content, payout, investment payout. What is your philosophy? Excess O2, and then of course the carbon tax. So there are so many things. But to give you a thumb rule, every 35-degree reduction in stack temperature will improve the efficiency by 1%. It's basically like every 20 degrees centigrade. To all my friends in India, it's 20 degrees centigrade. So if you reduce your flue gas temperature by 20 degrees centigrade, you will get 1% improvement. So let's focus on the design. When I'm as a designer, I'm working on fired heaters. The first thing which I look at is what is the fluid temperature, what fluid I'm heating, and what is the inlet temperature. So I have given here 6 different cases, and for basic heat transfer to occur, the flue gas temperature has to be higher than the feed temperature or the fluid temperature, because heat transfer requires a driving force. So in order to do that, my flue gas has to be higher than fluid. That's the number 1 rule. So if my fluid inlet temperature is 100 degrees, I have tremendous possibilities of heat transfer just with the fluid itself. And there is something which is known as flue gas approach. What is my approach? Because I want to do the heat transfer. The lower the approach, more heat transfer area I will have to put. Those of you who know Q is equal to UA delta T, and delta T is a log mean temperature difference. So it's basically, if I have 100 degrees, 200 degrees, I can make the heater efficient all the way to 90% without putting any air preheater or waste heat recovery, because I have very low temperature. So I can cool my flue gases straight away. If I have got 400 degrees, my flue gas leaving the heater has to be higher. So it is going to be 500, 600, And that's where the challenges start coming up. How do I reduce the flue gas temperature to 300 degrees or 400 degrees when my fluid inlet temperature is 600 or 800 degrees? And that's what we will talk about in this course, how to do it economically. I mean, remember, when we are doing fired heater designs, cost is the number 1 issue in designer's mind. He wants to give you the most economical fired heater, because if he gives you one guy is quoting $2 million, the other guy quotes $2.5 million, you will automatically disqualify him. You won't consider his offer. You will say the other guy is doing it for 2 million. Why are you charging me 2.5? And there are some heaters where the inlet temperature could be anywhere between 800 to 1000 degrees, and there we could be thinking about putting waste steam generation, waste heat recovery units, waste heat boilers generate steam. Those heaters are very good candidates for steam generation. Next thing which comes into play is the fuel gas cost. And in different parts of world, the fuel gas cost is very different. In US, the fuel is been range in the $2, $3, $4 per 1,000 standard cubic feet. Whereas in Europe, in India, in South Korea, rest of the places, the fuel gas cost is much, much higher. It could be $10, it could be $15 per standard cubic feet. So if the fuel gas cost is high, the savings are going to be high. So the higher efficiency will be justified. In US, the higher efficiency is not justifiable because the fuel gas cost is very low. So most of the furnaces in US are natural draft. 90% of the heaters in US are natural draft because the fuel gas cost is low. There is no incentive for the owners to put air preheating system or recover heat. Our hope is the gas goes up to high cost so that everybody is forced to put air preheat or forced to put heat recovery units and make their heaters more efficient, actually. And that will also help the emissions. Once you make this thing, you will get better emissions, lower emissions. Another is, what is the material of construction of fired heater? Is it carbon steel? Is it alloy steel? It is stainless steel. Because carbon steel is the most economical material, I would like to use low temperature approach for heat transfer. But if I have a stainless steel coil, stainless steel is at least 3 times more expensive than carbon steel. So I want to minimize my cost by using as little stainless steel as possible and maybe using waste heat recovery or air preheat to compensate for the efficiency. So as you see, a lot of things keep on going into play when we talk about fired heater design. How do I uh, produce the most competitive fired heater? Again, the payout periods. How much payout period? In US, the expectation is 1 to 3 years. You know, that's what they expect all the projects to pay out in 3 years maximum. Whereas in India, in Southeast Asia, they have long-term planning. So they say, okay, even if it pays out in 7 years, we will install the air preheat system or we will install waste heat recovery. So there are different norms in different places. There is no one such universal payback rule. I mean, everybody wants fast payback, but depends on the cost. So some people prefer low paybacks, but other people have a long-term planning, long-term issues. So this is a chart showing the thermal efficiency trends. We started 1960s, 75% used to be the highest thermal efficiency. And as you can see, in 50 years, we have gone to almost like 94. So any new heater which is being put now, especially anything more than 50 million BTUs or 10 million kilocalorie will have an air preheater. In fact, we have seen some inquiries from India where the heater duty is only 2 million kilocalories or 2.5 million kilocalories, and they are asking for 90% efficiency. So that speaks a lot, how which direction are we going, and that's really very, very good. Combustion air preheater is the most popular efficiency improvement system, and it reduces your fuel consumption straight away. By recovering heat from the flue gases, we preheat combustion air and feed that hot air into burners or into the radiant section. So we are recovering heat, and we can cool the flue gases down to about 300 degrees F or 150 degrees centigrade, go up to about 92% efficiency. That's a very, very common thing. A lot of people, they prefer steam generation, especially like steam methane reformers, ethylene crackers, where we find, so those can be very, very helpful, and they generate steam, And you can see here we have a boiler feed water preheater, steam superheater, steam generation coils, to generate steam actually. And we can again achieve 90 to 92% efficiency. In fact, we can add a process preheat coil in ethylene crackers over here, and we can go to about 94% efficiency. So we could do that. So that's the same thing what we have been talking about, waste heat recovery. We can have, this is a forced circulation system. We can have a natural circulation system. So let's talk about fuel efficiency. What does the fuel efficiency means? Fuel efficiency means the useful heat or the total heat absorbed, which is transferred to the fluid, divided by the fuel input, how much heat we are firing. Now, in a lot of cases, we cannot measure the heat absorbed in the process because of two-phase flow, because of reactions. So what we do is we say, okay, the total heat absorbed is indirectly how much heat I have input and how much heat is lost. And basically the difference between the two is my total heat absorption. That is an assumption which has been made, and it works very well for most of the cases. So this is a formula. I think we have a heating value, air sensible heat, fuel sensible heat, and if we have atomization media, then the atomization media. And then the losses are radiant heat losses and stack heat losses divided by the heating value of the fuel. So that is how the fuel efficiency is defined. The fuels typically have two efficiencies defined. They have higher heating value when you take the products of combustion and cool them down, and water in the flue gases condense, giving additional heat. That is known as higher heating value. Higher heating value is used in the utility industry. Lower heating value is when the products of combustion remain in gas phase, and that is used in the process industry. And it is expressed mostly as kilocalorie per kg, kilocalorie per meter cube, or BTU. So I have these combustion calculations. Let's go over them, see how many slides we can cover. So let's do some of this heat balance. My colleague has done it. So thermal efficiency needed is 90%. Inlet fluid temperature is 480. I select an approach of 200 degrees. So my flue gas temperature leaving the convection is 680. There is a reason I will tell you later why I selected an approach of 200 degrees. So now with 600 degree, 680 degree, I know I cannot get 90%, so I go for an air preheater. API says you have to take heat losses of about 2.5% with air preheating systems. So we come up with an air preheater which cools flue gases from 680 to 365 and preheats the air from 60 degree to 435 degrees. My air preheater duty is about 11.3 million BTUs, and my calculated thermal efficiency is about 90%. So I'm able to match it. I'm able to meet the requirements. Let's take another case. So in this case, I say, okay, I still want 90% efficiency. My inlet fluid is again this thing, but I want to use 100 degree approach. Instead of 200 degree approach, I change it to 100 degrees approach. So now the flue gas temperature leaving convection is 580. And as I do that, I still need an air preheater. I had to get 2.5% heat loss. I still cool the flue gases to same temperature, but my air preheat temperature is much lower, 312 degrees and 7.6 million. So why would I do that? Why would I do this? Now, as you know, a lot of times we get into NOx emissions limits, and higher air temperature leads to more NOx. So if I'm going for NOx limits, I want to keep the air temperature to minimum preheated air temperature. So I may go with a lower air preheat to get my NOx emissions. So that's another factor comes into play actually. Can we do that? This is another case where the client says, I want 92% efficiency. And we say, okay, we can do that. And here I have taken an approach of 300 degrees. And this, I could be doing that if my material of construction in the heater is not carbon steel, but alloy steel or stainless steel, which is expensive. So I want to minimize the area in those coils and maximize the area in air preheater, because air preheater is made out of carbon steel. So I try to keep maximum approach. My flue gas temperature is about 780 here. Heat loss is still 2.5%, but I end up having a much larger air preheater. And you see, my air temperature goes up from some 300 this thing to 640 now. So I will be making more NOx, but if I can meet the emissions limit, this design will work as well actually. So you can see we can come up with different options. This is another option where the minimum efficiency specified is not 90%, but 85%. So with 85%, I said, okay, I don't need to put an air preheater. I put inlet temperature of 480. I put a 50-degree approach. And when I put a 50-degree approach, I get 530 degrees this thing. And with 1.5% heat loss, I'm able to get about 87%. So as I said, most of the heaters in US are natural draft. I mean that they are still pretty efficient actually. They could be more efficient, but they're still pretty efficient. And we can get up to 87% efficiency in this case. So efficiency combustion is a very important first step calculation which we do in fired heater design. Uh, so this is the problem which we wanted to talk about. And you can see we took this thing and we did methane, ethane, hydrogen combustion. So then we do the basic combustion calculations. Methane gets converted into carbon dioxide and water vapor. Ethane also gets converted, but if you look at the differences and how many moles, it needs 2 moles, ethane needs 3.5 moles. Similarly, ethylene needs 3 actually, and what hydrogen needs 1. So we write these individual equations, and then we do these stoichiometric calculations. How many moles of air or oxygen is needed, and then we come up with this number and do this chemistry calculations, stoichiometric calculations, calculate the air required, and then we calculate the excess, what percent excess is needed. So we come up with this heating value first. What is the weight percent? So we do this calculations, how much flue gas is generated in each reaction. We do that. And most of these calculations these days are done by computers on Excel spreadsheets. So we do this, we do the fuel gas heating calculations, and we come up with this type of summary, how much fuel we are firing, how much total air flow rate, how much is the total flue gas flow rate, flue gas to fuel ratio, approximately 20 pounds per pound of fuel. What is the heating value? What is the higher heating value? So we do all these calculations, which are generally done by computers, and then we come up with this fuel efficiency. This, I think we already presented this formula. So we calculate the heat losses, radiation heat losses, how much is the heat loss. We calculate the stack heat loss depending on the temperatures. And in each case, it is different. When it is 365, it is 1581. When it is 285, it's higher. But when it is 530, it's even, it's lower, this is higher. So we do this, and then we come up with the efficiencies, So it's a pretty, it's simple, actually, simple chemical calculations, chemistry calculations, and that's what we do. But as I tried to show you, we have so many different parameters to talk about. So we will continue our discussion next month, and we will start focusing on the radiant section, which is the most important component in any fired heater, where the heat transfer takes place because of radiation properties of carbon dioxide and water vapor. So we will talk about those. Please do give me your feedback. Tell me what we can improve in our next webinar, and whether you like that, whether you like the new format, the new timing, and we will go from there. Thank you very much. You can send me your questions by email, and we will be more than happy to answer them on our website, on our webinars, on our Facebook page, LinkedIn page. And again, thank you very much for giving us an opportunity and for giving me a patient hearing. Have a nice day, nice evening, and enjoy. Stay safe. Thank you.